So Bohr's model was great. It was a fairly simple model. It gave good theoretical correlation with the experimental evidence that was available. Unfortunately, as scientists began to consider more complicated atoms, that is, atoms with more electrons, a number of problems arose, one of which is described as the Heisenberg uncertainty principle. And briefly, what that means is that there is a fundamental limit on how well that we can measure both the position and momentum of a particle, in our case an electron, at any time. And if you can't be sure of both the position and essentially where the electron is going, then it's very hard to maintain a model which has as its fundamental feature a well-defined orbit like what we had with the Bohr model. So, in order to solve some of the problems that came about with the Bohr model and to deal with this idea of uncertainty, the quantum mechanical model of the atom was developed. And the quantum mechanical model is a mathematical model that can be interpreted as giving information about the probability of finding electrons at any particular point. So in this diagram, what we have is the probability of finding an electron at some particular distance from the nucleus. And you have two different ways that you can represent this. One is this kind of graphical way. Let me see if I can find my little pointer gadget. Is that it? It is my pointer. So where you plot the probability versus the distance. And the other is where you let the darkness of the color represent the higher or represent the probability of finding the electron at some particular position. Another way to think about the probability is to calculate something called the radial probability, so that while with the essentially what was the linear probability, you found the probability at any particular point individually for an electron to be found. With a radial probability, what you are looking at, it's a little hard to explain, but if you imagine drawing very narrow spheres around the nucleus, and then you calculated the probability of finding an electron in any of these regions. So this is more like the total probability of finding the electron within one of these concentric spheres. Then that's referred to as the radial probability. So you are not really expected to understand how to derive the relationship between the Schrodinger equation and the electron probabilities. What you do need to know is that the orbital can be thought of as a three-dimensional electron density map, where the intensity or darkness of the color is proportional to the probability of finding an electron. And what happens is that it's actually possible to solve the Schrodinger equation or the wave equation for hydrogen very accurately because it just has a single electron. In order to apply the model to electrons or atoms, that have more than one electron, then you just extend and modify the idea for hydrogen a little bit, and we'll see how that works out in the next couple of slides. So this brings us to quantum numbers, and quantum numbers are a set of numbers that describe the various shapes and energy levels of an orientation in space of electrons within an atom. You'll see in a little bit that they are very comparable to the electron configurations that we wrote, but this is just kind of another way of indicating this same information. So there are three quantum numbers to begin with. So you have the principal number, which is referred to as n, and that's the size and energy of the orbital. You have what is referred to as the angular momentum quantum number, L, and that is the shape, or sometimes referred to as the subshell. And then you have the magnetic quantum number, and that number indicates the orientation in space of the orbital relative to other orbitals in the atom. So here is a chart which really summarizes all this information. So I will take a few minutes and go through this just to try to make sense of it for you. So over to the left over here we have the principal numbers 1, 2, 3, 4, 5, 6, 7, and the quantum number, the second quantum number L, has a definite relationship to the first quantum number, and essentially L can have values that are from 0 to n minus 1. Okay, so when n is 1, L can only be 0. When n is 2, L can be 0 and 1. When n is 3, L can have values of 0, 1, 2. And when n is 4, you can have values for L of 0, 1, 2, 3. So they go from 0 through n minus 1. This in column, okay, indicates the sort of corresponding way of describing these with electron configurations. So that 0, for example, is corresponds to S, and 1 corresponds to P, and 2 corresponds to D, and 3 corresponds to F. Okay. Then the magnetic quantum number M is related to quantum number L. So M can have values of that go from minus L through 0 to plus L. So again, with the first level, you only have 0. There's not really another possibility there. And with the quantum number 1, then you can have minus 1, 0, plus 1. When you get to quantum number 2, then for L, or L equals 2, then you can have minus 2, minus 1, 0, 1, and 2. And this is corresponds to what we wrote out as orbitals back when we were talking about electron configurations. So the first sublevel S can have one orbital. The second sublevel, which we called P, can have 3. This would correspond to an L value of 1. D can have 5 orbitals, and F can have 7. Okay, so for this question, it's asking if you have the quantum number 3, principal quantum number 3, then what are the allowed values for L? So L can range from 0 to n minus 1. So that means that L can have values of 0, oops, not wrong utensil there, 0 and 1 and 2. So those are the essentially the sub-levels or subshells. So this would be S, this would be P, and 2 would be D. For L equals 2, then we have values of the ML, the third quantum number, that can range from minus 2, minus 1, 0, plus 1, plus 2. This would correspond to the 5 orbitals that we originally talked about with a D sublevel. So if we look, this is the typical representation for an S orbital, 1s, 2s, so they're the same basic shape, but they are a different size. When we look in more detail, what we see is that there are actually these nodes, these areas of 0 probability between the different interior probability distributions. So, for example, with the 1s, we don't really have a node, but in the 2s, we have a node, and in the 3s, we have 2 nodes. You basically have whatever the number is minus 1 number of nodes, and then this representation up here just shows it's just another sort of graphical way of looking at that. For the most part, that's not going to play a big part in what we are discussing. We usually just use these basic shapes. And here are representations of the p orbitals. And this is, you can imagine an experiment where over time you put a point down each time that the electron sort of was in a particular region, or you marked its location over time. So that is simplified to give these sort of, sometimes they're called dumbbells. They're not really dumbbells, but I don't know what you want to call them other than that. These other representations of the p orbitals. And notice that the p orbitals are centered around an axis and that they are mutually perpendicular in space. This is actually going to turn out to be important when we talk about shapes of molecules, so sort of keep that in mind for later discussion. And here are the Ds. The Ds we're not so concerned with. We do get bonding in with the d orbitals, but for the most part we're concerned with what's going on with the s and the p. And you can see that the Ds are just a bit more complicated and kind of unusual looking, especially this one down here, compared to the s and p orbitals. So finally, there is the fourth quantum number, which is a spin quantum number, and that indicates that in a particular orbital you can have a maximum of 2 electrons, and those electrons have to have opposite spins, so you can think of it as clockwise, counterclockwise, just 2 different spins. And that is referred to as the Pauli exclusion principle. I mean, obviously most of the atoms that we're going to deal with are going to have more than 1 electron, so how do we work with that? So there is a problem, and the problem is that since we don't understand the pathways of the electrons, it's very hard to calculate the repulsions, which we would need to do in order to make the model specific. So there are just some guidelines that have been discovered as far as, for example, the order that the orbitals fill. So you may recall that we said that S was lower, or fills first, P, D, and then F. So as I said previously, the S is going to be lower in energy than the P, and the reason for that, or the explanation for that, has to do with what is referred to as penetration. So the S orbital has a probability that is higher, nearer to the nucleus, and shields the p electrons somewhat, making them a little higher in energy. So I'll show you that in the next slide. So here we have again this radio probability graph. And this is what I was talking about. So this is part of the 2s, and you see there's a part of the radio probability that is higher, closer to the nucleus. So it's as if, or not as if, these electrons are shielding the p electrons, even though on average the p, most of the p is actually lower in energy. The shielding that occurs due to these electrons causes the p electrons to have a greater energy than the s electrons. And you can apply the same thing all the way through, so I'll just show you a couple more examples. Okay, so this is a representation for the 3s orbital. And remember before, so when I was talking about nodes, so that's a node, and that's a node, and then we have these small but significant areas where we find the 3s electrons. So when we look at and we sort of superimpose what's going on for the 3s, the 3p, and the 3d. So here we have the 3s, which is shielding the 3p, which is shielding the 3d. So that's the explanation for the difference in the order of filling those particular levels.